All right. Up next, we have Professor Kim Boddy, who's a professor here at University of Texas at Austin, and she'll be talking to us about dark matter in the context of cosmology.
Thank you very much. Okay, so this talk will be about using cosmological observables to see what we can understand about the fundamental nature of dark matter. And I realize that I'm the first assistant professor here that is talking locally, so I'm going to set the stage for my fellow assistant professors for Saturday. So please do come and see their talks, and I'll highlight some of their work in my talk as well. So where I want to begin is post inflation. I want to think about, okay, I already have all of my initial perturbations that are set in, and the inflaton field is going to give me my perturbations in the fields that make up the standard model today. So for my temperature perturbations, we can view these from observations of the cosmic microwave background when the universe recombines and the photons are able to free stream to us today. The universe is very homogeneous and very isotropic, and it has a temperature of about 2.7 Kelvin, but there are these very, very small, tiny perturbations that are associated with the perturbations that come from the inflaton field. And so we can look at maps of the CMB temperature and polarization of the CMB photons, and create these two-point correlation functions, these power spectra of temperature and polarization as a function of angular scale in the sky. And so over here, this is angular scale and it's going down to the right. You can imagine taking these maps of the sky and decomposing this into multipoles. And so this is the multipoles, this is your YLMs. The multipole L gets larger as you go to smaller and smaller scales. And so the power of the CMB is that it has a lot of information. So the smaller angular scales that we can go down to, the more information that we have. And there's a lot contained in here. And so this has provided us with one of the most precise measurements in cosmology that we have. And it has informed us quite a bit about the content of the universe, as well as what it's doing. So in terms of what the composition of our universe is today, it tells us that most of it, present day, is in the form of dark energy, right? That is the reason for the accelerated expansion of the universe presently, and that most of the matter is in a form of dark matter. It is not the standard baryons that make up you and me and everything that you can find on the periodic table. And so this large portion that has to behave like matter but doesn't interact with photons isn't any one of our standard model particles, right? This chunk here is not understood, right? We don't know what its mass is. We don't know what its spin is. We don't know anything about it, what its interactions are, if it's even a particle. And so this is the program of a lot of different subfields in physics, is to try to understand how to approach this dark matter problem and figure out what its properties are. And this is important given how much of the universe is in the form of dark matter. And so this is going to be one instance where, yes, this is going to be an instance where Windows clearly did better than Macs because the video will not play. So I'm going to bring my screen over here and show you what dark matter does as soon as you essentially let these very, very small density perturbations that we see in the CMB, let them evolve over time. And so this is a simulation where people have taken these dark matter particles. And so everything is very, very smooth looking, very homogeneous looking, but dark matter is going to gravitationally interact. It's going to cluster. And so as it clusters, it starts forming these beautiful, intricate structures. So this is the cosmic web of our universe. And these individual structures are able to attract matter, normal matter, and be able to host star formation and galaxy formation, as we heard from Netta earlier. So, right, and so this is advancing in terms of time. This is time after the Big Bang in gigayears, and you see the corresponding red shift. And so all of this is just a dark matter only simulation, but it's showing you where all of the dark matter is clustering. And so you see this really beautiful structure that dark matter is able to provide. Now, I think we can actually, for the sake of time, just go ahead and stop this. Bring this back here. Okay, and so, right, so we had this, this dark matter field that was in the early universe. It gives us our cosmic structure that we have today. We can go out and observationally see that there is some sort of matter that is non-luminous, that does give rise to, say, gravitational lensing, and explains our velocity rotation curves, that each galaxy clearly needs more matter than we can see to explain how fast the stars are rotating around it. Okay. The way that we can simplify this picture and talk about it simply is to say how much matter is there at certain scales, essentially. So this is the matter power spectrum, and it's showing you how much matter there is in inverse megaparsec down here. So these are data points from a whole bunch of different probes. And so the CMB, the Planck satellite, is able to constrain what the matter power spectrum is. And so this story of having just dark matter, the majority dark matter, some baryons, and dark energy really fit all of this data very, very well. Okay, so the standard cosmological story.
I'm going to interrupt just to say that you're showing work with astronomy professors here, which is great. I'm going to just say who they are. So Mike Boyle and Colton made that video, and he was the chair at the last session. And here we have Julian Munoz. Maybe you were going to say it, our assistant professor that he was at the top of the short list of both physics and astronomy. He ended up in astronomy, and he's speaking later during this conference. And forgive me for interrupting.
Yes, but thank you. That was a good point. I did want to mention that Mike, he was cited in an earlier slide. But yes, Mike was responsible for the Millennium 2 simulation that I showed earlier. And so this matter power spectrum is telling us how much matter there is at certain scales. But these scales, and this does come from work that Julian did, and these scales, though, as you get to smaller and smaller scales, which means higher and higher wave number, right? As you get to smaller and smaller scales, these modes in the early universe become nonlinear, and so you have to do this treatment of running these simulations that I showed that Mike does to understand the gravitational clustering and properties from these particular scales. Okay, so that's by and large what dark matter is and what it's doing for our universe and the evolution of our universe. This is all under a very, very simplified picture, right? Where dark matter is just some matter fluid. It doesn't have any communication other than through gravity with any other particle, with any of the standard model particles, and specifically it's cold, right? And when I say cold, I mean it can gravitationally cluster when it wants to infall into its potentials. It doesn't have enough energy to stream out. Okay, so all right, so we have this dark matter. What is it? What is it? What are its properties? How do we go about as particle physicists and saying, what can we do with this information? And there's this very, very nice, beautiful story called Weakly Interacting Massive Particles, or WIMPs. Okay, and it's very simple. You have dark matter particles and standard model particles. They can interact with one another. And you can imagine in the early universe, when everything was hot, dense, relativistic, that you had dark matter and standard model, that they could somehow communicate with one another through non-gravitational interactions. And if you were able to have this happen, then you would have both the production and annihilation of dark matter particles with the standard model bath. And the standard story that we learn nowadays, in terms of what dark matter freeze out is that as the dark matter becomes non-relativistic, its density will start decreasing exponentially. And then eventually it will just stop and freeze out because the Hubble expansion has essentially made the annihilation interactions inefficient. And so the name of the game is trying to get the right annihilation cross-section in order to explain the present day density of the universe. And it just so happens that if you take a standard cross-section that scales as coupling squared over mass, or alpha squared over mass, that you can get the right relic abundance if you have weak scale interactions and weak scale particles. And so this fit all very nicely into a picture, a larger framework of supersymmetry. If we had the lightest supersymmetric particle of the standard model, this could be a great candidate. It has weak scale interactions, weak scale mass, and this could be dark matter. It also has very properties that we want from cold dark matter to explain all the observations that we've seen and tell this beautiful story that we discussed before. And so there's been a very long and dedicated process to trying to find and understand WIMPs. Okay, and so there are various channels of which we could go and search for WIMPs. One possibility is that we produce them at colliders, and we can look for, say, missing energy at the LHC. And this is where two standard model particles are going to collide, two proton, and produce missing energy. You can imagine having annihilation. So we could go out and take telescopes and look to see where we know dark matter should be astrophysically. And we can say, okay, we're looking for annihilation products of dark matter into standard model, say, photons. And that would be something that is not astrophysically explainable that we can attribute to dark matter physics. Another option is through scattering, so through direct detection methods, where we have a big, huge container of, say, liquid xenon. We place it deep underground, and we say, we expect this dark matter particle to come in and hit one of our xenon atoms, and we will look for the nuclear recoil of that atom. And so this is direct detection, and these programs have been going on for a very long time. And so direct detection experiments, for instance, have attained extremely great sensitivity. So this is a plot of the dark matter cross-section with nucleons as a function of the dark matter mass in GeV. And so you can see there's a whole bunch of experiments. This is certainly not all of them. This may not even be the most up-to-date thing. And it is actually certainly not the most up-to-date plot, but we have a whole bunch of different experiments that are going and pushing this interaction cross-section down and down and down, which is what we expect for weak scale interactions, right? There is a little bit of a limiting factor here. The direct detection experiments have some ceiling. If the cross-section is too large, then you have to have dark matter particles traverse the atmosphere, traverse the Earth in order to even get to your detector. And so if the interaction cross-section is too high, those particles won't be able to do that, actually be seen in your detector. There's also a mass threshold, that there has to be a certain amount of momentum transfer that the dark matter imparts to the particles. And if that's not enough energy, then it's essentially below threshold for these experiments. So you can do that, and you can try to play the game of pushing to lower masses by, say, considering dark matter scattering with electrons. And so notice that this scale change, now this is an MeV, but ultimately, there is still the same issue, that they can only go down to a certain mass. So this is a story of direct detection. Indirect detection, there's a wide landscape of things that have been probed. So across many, many orders of magnitude in terms of the photon energy that dark matter could produce and leave a signal in one of these ground-based or space-based telescopes. And so this is a wide area of active research as well. Okay. So this is a large energy range corresponding to a very large mass range of dark matter. But let me even take a step further back and say there's an even wider mass range of possibilities for dark matter. And there are well-motivated candidates that go down to very, very small dark matter masses. We're talking 10 to the minus, say, 19 eV, right? And these candidates down here would be so light that they should actually have wave-like properties, not particle-like properties in our galaxy. You could alternatively go and say maybe dark matter is not a particle, maybe it's some massive object like a primordial black hole. And this was a plot that was made in 2017 that a handful of us got together and made this US Cosmic Visions report. And there are a whole bunch of different models, some lab experiments, and cosmology and astrophysics was the tiniest portion of this report in 2017. And since then, the cosmology and astrophysics for this field has exploded. And there have been a lot of new progress. There's been a lot of new research directions and progress that have been made utilizing the cosmos. And so I want to go back to this picture about what the typical WIMP searches look like and say that instead of thinking about colliders, we can think about getting the right, relic abundance for dark matter. That's sort of the same story that we had before for freeze out. But for annihilation, we can think about, oh, if dark matter is around and it annihilates in the early universe, that injects energy or entropy into the standard model sector. And that should be observable somehow, right? Through our cosmological observables. You can also have the process of scattering. So if dark matter is able to scatter just even elastically with a standard model particle, say a baryon or a photon, or even a neutrino, that this is going to have an effect. It's going to transfer momentum between these two species, and that will affect how dark matter behaves. And if you affect how dark matter behaves, then that goes and affects every single thing that we know about the evolution of structure formation. And so we can go out and test for these types of models in this way. So for the rest of the talk, I'll go and do a little bit of a grab bag of possibilities of where you could use cosmology to search for new physics related to dark matter. So I'll start very early, what I call very, very early, which is BBN at the earliest. But BBN and CMB, when we have our Big Bang nucleosynthesis. And so everything that is related to BBN and related to the CMB depends on how fast the universe is expanding at any given time. And how fast the universe is expanding depends on the content of the universe. And so we talk about this quantity called ineffective. It is essentially the effective number of neutrino species that we have, because neutrinos are non-relative, or sorry, they're relativistic. And we compare that to how much energy density are neutrinos in comparison to photons. And so this ineffective is nominally about 3, because we have 3 neutrino species, and we can ask the question, do we see any deviation away from this expected 3? And the answer is that it's pretty constraining. So, Planck data, and you combine that with BBN predictions of nucleosynthesis, constrain this value of ineffective to be pretty consistent with 3, but there are error bars, and so there's some wiggle room. And, future, say, CMB experiments like Simon's Observatory, like we'll hear from Nick, or CMBS4, which I'm a part of, is going to narrow down these error bars. And we can tell if there's some new species that doesn't nominally belong, that could belong to the dark matter sector. Okay. With the CMB itself, with the anisotropies, we can imagine injecting energy into the plasma post recombination, or allowing for some scattering to happen. In both cases, I won't go over the details here, but in both cases, you take the nominal power spectrum for the CMB, which fits the data very, very well. We can turn on a lot of annihilation or a lot of scattering, and it just suppresses this whole curve. And so that's something that we can search for, and something that we can constrain. And let me just skip this slide. This slide is just to say that I was a trained proper particle physicist, and so I do use Lagrangians. That's the only thing I wanted to say there. But the Planck CMB constraints on these two different types of processes show some nice complementarity between the traditional searches and what we do in cosmology. So here is the annihilation cross-section as a function of mass. The Planck satellite is able to place a bound on the annihilation cross-section, and that's all shaded here in tan. But you can see where other experiments and other observations have kind of come into play, and they're fairly comparable. So the CMB does a very good job of constraining the amount of energy that's injected into the primordial plasma. For scattering, so here's the dark matter nucleon cross-section as a function of dark matter mass. This is in an area of parameter space, which is very inaccessible to direct detection experiments. And so it's at much higher cross-section, and it can extend to much lower masses. Okay. We can take, for instance, these limits from the CMB on scattering, combine them with limits that we have for, say, not wanting to have too many effective neutrino species at the time of BBN, and we can get joint constraints on these two processes together. Okay, so my collaborators and I did this work recently. I do want to share that one of my collaborators was very excited about having us on this project to be on Boddy and Glucovic so that we could be alpha, beta, gamma. That makes me beta. I don't know how I feel about that, but at any rate, this is some work that was led by our colleagues at USC. So another aspect going beyond the CMB now comes into this structure formation, right? So I showed you this nice video that Mike made of clustering of dark matter and forming structure. This is the plot that I showed before, the matter power spectrum. And all sorts of different interesting dark matter physics can mess with this, right? And so here's another way of displaying this same plot on the left. I'm just multiplying by a scale by k cubed to make this more or less flat out here. And you can see that for a whole assortment of models that I won't go into detail about, but a lot of them give a suppression of the matter power spectrum, right? The most common, the one that has been around the longest, is called warm dark matter. So it's where you have dark matter and it's not completely cold. So it doesn't just cluster and stay there, but it will cluster a little bit and then stream out of potential wells. And so this warm dark matter case is something that will suppress power on small scales. If you have this scattering process that I talked about, that can also suppress power on small scales. So what does that mean observationally for us? So this means that if we were to take a simulation of just ordinary cold dark matter, this is dark matter only simulation, and we have some large dark matter halo that would host a large galaxy. And we see all of this tiny little structures dotted in here, right? And this is all the tiny smaller scale structures that we're able to form in the simulation. And if you put in this suppression of the matter power spectrum, very generally, this is what it does. It just washes out all of this nice structure that has formed, and you're just left with the larger halo that is going to host the larger galaxy. So what is an example that we can apply to this that gets to the smallest scale structures that we can observe? And this is our own Milky Way. And in our own Milky Way, so here's the visible Milky Way, here's the Milky Way halo, we have satellite galaxies. So these small dwarf spheroidal galaxies have dark matter halos of their own, and they orbit the Milky Way. The Sloan Digital Sky Survey, which we heard earlier, Pan-STARRS, DES, the Dark Energy Survey, all have seen a whole bunch of these very, very faint satellite galaxies. And the fact that they are even in our Milky Way tells us that dark matter can't have washed away that structure at early times. They have to exist. So this is going to be able to essentially place a bound on how much dark matter can interact with the standard model. So here I'm showing on the left just a suppression of this matter power spectrum with respect to lambda CDM. And so you just see this sharp cutoff. It's for a couple different models that we have here. And this goes and affects how many subhalos or satellite galaxies that we expect to see with respect to lambda CDM. So this is as a function of mass. And you can see as we go to smaller masses, the number of subhalos that we expect is much, much smaller. But of course, we have observations of this. We have, DS, Pan-STARRS, and we can say that, well, we know what the luminosity function is. We know where those stars are in these satellite galaxies. And barring some modeling uncertainty that has to do with how many baryons do you expect, or how many stars do you expect in each satellite galaxy, we can place constraints based on this data. Okay, so that's great. That was all very hand-wavy in some sense, but how does this relate to the actual nature of dark matter? And it relates because depending on what you choose for the dark matter mass, what you choose for how much it interacts, or if it's warm dark matter, how warm is it? Those fundamental properties go and have a very different effect on what the matter power spectrum or the suppression of the matter power spectrum looks like. And so we can go ahead and essentially take these curves that we can produce theoretically, we can compare with data, and generate constraints in the parameter space of, say, dark matter proton scattering as a function of dark matter mass. So here, these are very large cross sections, right? And so here was the CMB line that I showed you before for a particular model. This is direct detection. So direct detection is placing a bound way down here somewhere. But at very high cross sections, there is a ceiling, there's a limit to what direct detection can do. The constraint from having the existence of the Milky Way satellites and their population is shown here. And so this was work led by Risa Wexler's student and we'll hear from Risa later in this conference. So this was a lot of fun to work with them and to do this work. So this was only an example of just showing, dark matter baryon scattering. I could have chosen any other sort of scattering scenario. There's been a lot of work on dark matter neutrino scattering. You can think about dark matter photon scattering, and all of these things constrain or are constrainable through cosmological observations. So there's this very nice complementarity that we have between different cosmological probes. So here's the CMB, here are the Milky Way satellites. That's a huge difference. The CMB is blown out of the water by Milky Way satellite constraints, but this is for one particular model, right? And so it's going to depend on what scale, what energies you're looking at, what time in cosmic history you're looking at, to identify which probe is going to be the most sensitive to your particular favorite model. And so this is summarized here in this plot. This is redshift at the on the x-axis, and essentially scale or halo mass on the y-axis. And this is just trying to demonstrate where various observations lie in terms of their ability to constrain dark matter physics. And so the coverage here is complementary to each other. And we have the CMB probes that I discussed to you today, as well as dwarf galaxies. But there is a lot in between. And so quite a number of us here at UT Austin work on all of these things that I didn't have time to actually go into. But these are probes, and we have new experiments. We have new satellites that are being built or have been built to go and help us probe more sensitively the nature of dark matter. So the way that I want to end is to once again highlight the cosmology portion of the Weinberg Institute. This is the faculty in physics, the faculty who are in the astronomy department, as well as my own group. And so we have some postdocs at the top, students at the bottom. This is particularly my group, as well as students and postdocs who I work with in the rest of the Weinberg Institute. So with that, I will end and take any questions.
All right. Any questions?
For this, for the satellite galaxies that you do, we only see those that have some stars. The stellar function is very low. There could be many that don't have any stars in them. How do you take that into account?
Yes, that's an excellent point. So we can only go down to where we actually have something to observe with any sort of galaxy survey. So you have to get a little bit more creative if you want to see substructure that is below the star formation threshold. So you can do this with, you can think about doing this with microlensing. You can think about doing this with, people have thought about how stellar streams, how you could have some small but dense structure that could be related to dark matter could be disrupting stellar streams. And so you do have to get much more creative when you don't actually have stars to see. Yeah, I'm personally, but there's a whole other program of people who work on very complicated simulations of stellar streams, and that field is pretty young and has a ways to go. But that's also a very interesting future direction.
All right, thank you. Head on to the next speaker now. Stay on time.